Yeah, thank you, Fabian, and thank you everyone for organizing, bringing together this very nice conference. Yeah, so today I'll talk about something I'm actually very excited about. So this is work done in collaboration with these people. So this is Michael Spanowski in Durham. Then there is Samuel Towie from Stuttgart. He's a PhD student. Konstantin Nicolaou, who is also a starting PhD student in Stuttgart, and their respective supervisor, Christian Holl. And this is two papers which have already appeared and are published, and work in progress. So to set the scene a little bit, let's ask the question, okay, what we really need to solve and what is going on. And there are actually big problems in neural networks, and I think physics can help in this problem. So what are they? Well, they are, if we think about our big language models, the big problem that we cannot afford our typical hyperparameter scans, given by basically by the cost and maybe also the energy that is used to train these things on the one side, but on the other side of things, we should also always be reminded that what we're actually doing on the left-hand side is rather inefficient and is probably not the best thing that is out there if we compare it with biological systems. And in this regard, this has been obviously a long-standing problem in this community. That the question, how do we improve the efficiency of neural networks? And the idea and overall scheme is that we want to describe neural networks and their dynamics as effective field theories. Why do we want to do this? Is basically because neural networks are nonlinear systems, and we need to understand their dynamics in order to answer these big questions. And we have actually a very nice hammer around as physicists, namely we have around effective field theories that describe nonlinear dynamics. So putting this more concretely, what we're interested in is to describe the dynamics by field theories, and then to really understand what how is this field theory determined, and by the underlying neural network and the respective dynamics. So concretely, this means to understand how the architecture, how the data that we use, how the optimizer and the loss function all play together to determine our field theory. And these are, for us, very interesting because they are nonlinear but understandable models with relatively few collective variables as degrees of freedom. And I think they're exciting for two reasons. One, this approach is because we can obviously use these models to make our neural networks more efficient. But also for physics, because they might give us then an insight once we understand them nicely to look at physical systems from a different angle. And I say understandable models here because by physicists, because this is a recurring scheme, and there has been a lot of activity also in this conference about using such methods in the understanding of neural networks. To list a few. So what do we want to do? Well, we want to identify a perturbative description of neural networks. And what we work with is neural networks at large width and the empirical neural tangent kernel in the first instance. In the first step, we want to understand the field theory description that is underlying this, and how do the different components, in particular the data architecture and optimizer choices, affect this. And I will talk about one application that then already emerges out of this, is namely making our training much more data efficient. And then once you have this nonlinear framework, you can start thinking about doing model building using these collective variables. and I'm excited to talk a little bit about how we can use them to build dynamical optimizers, building in this bias of the neurotension kernel spectrum. So let's set the scene a little bit on how field theories and neural networks are connected. And basically, I mean, we could put it plainly. They are both their functions effectively. They take some input, and you know, they probably evolve in time because they're dynamical. You know, we train them, but we can go more specific about these things. And in that sense, one thing that you know, we can often think about quantum fields or field theories is by looking at them in particular mode expansion. And in that sense, that is somewhat very resemblant of what kind of parameters one is having in neural networks. In general, what we often do in physics when we describe field theories is that we do some perturbative expansion. For instance, we can expand it around some mean field and look at perturbations around it. And as I will argue, this is very much a similar thing we can do in terms of mode decomposition of the neural tension curve. But this is obviously not everything. What you also want to know is you want to know dynamics. And just to give you a little bit of a cartoon picture of what is often going on is if you have some UV model, say 5⁴ theory, for instance, and you know, some initial conditions, what can happen, for instance, you know, if you think about scalar field dynamics, is you start with some initial conditions, and due to that action, they do evolve. And you end up with a different field configuration. In some sense, that's what we want to match to what happens on the neural network side when we do training, subject to some loss function and some optimization. So how do we do this? How do we link these dynamics? And there's a nice framework which is that neural tension kernel that I would like to spend a few minutes discussing. And it is nice because it is not just on the theory side, but it's also on the practical side. When you apply it, it gives you very nice results. So what you're looking at is a simple, so in this case here, a simple update equation with stochastic gradient descent. And the object of interest is, where is this going? Is that the, if you're looking at the function f dot, the update of your neural network, you can rewrite it by just using chain rule, and you get this object capital theta, which is the empirical neural tension kernel. As you can see, this is an n by n matrix where n is the number of data points that you use to evaluate this. And what the observation is that in the large width limit, this neural tangent kernel remains constant throughout training. And so this is something, for instance, what is shown on the right, where these plots are taken from earlier papers, is to compare this with actual neural network dynamics. And you see that they, at least if you compare the loss respectively and the accuracy, that they do match, and they do match things like double descent and so on. So this is very, very nice in this limit. The other very nice thing about this story is that this includes everything, right? So this includes finite data, this includes optimizers, and this includes the architecture itself. However, we do know that this is not sufficient, because when we do experiments, we do see deviations, and we do see that there's a time evolution of these. And so the question is, okay, which simple models describe these dynamics? And then it makes sense to look at this object a little bit more in detail. And so one thing you can look at is you can look at the spectrum of of this object. And so I'm showing this to you here on the right-hand side for some dense and convolutional, simple dense and convolutional neural networks. And you do see certain hierarchical properties. Namely, you see one very large eigenvalue, and then you see suppression of the further the additional eigenvalues. And this has obviously consequences that have been noted also actually before. Namely that if you only have a few large eigenvalues, if you diagonalize this update equation, it means basically that the largest updates are associated to the largest eigenvalues. And if you only have a few non-vanishing ones, then you actually only update in these directions. And so this is effectively the dynamics take place in a lower dimensional subspace. And so this means that there are actually a few collective variables in this which determine the dynamics. And this is the time evolution is what we need to understand. And there's another interesting aspect to this story, is because you can evaluate this obviously at more and more data points, and you see you're adding basically vanishing eigenvalues to the spectrum. And so that means that they become rather unimportant. And so you have a nice limit on going between finite and infinite data limit in this story. Now let's look at want to understand this and to match this with physical systems. And to do this, I don't like to think about first order systems. I like to think about if I have a second order differential equation around, it's easier for me. And this can be done. So if you look at the update equation, in the case of adding momentum, you end up with a second order differential equation. And this is written to you here. And so this is something I can ask, okay, yeah, where in physical systems do I actually see this? And this brings me to one physical systems that we obviously love in our field. And that is scalar fields in cosmology. And so let's give you a little bit of a theory on this side. Some of you obviously know this very well. So what we're looking at is a scalar field within a particular background metric, which is dynamical. So this is Einstein-Hilbert plus this scalar field action. And if you look at the equations of motion that you're getting for this, this is shown to you here. And what we often do in this analysis is we actually do a perturbative analysis in this background. Namely, we look at a mean field and we look at perturbations around it, and we see how they do evolve. And this is something you can obviously study, and you can study their growth, and you can study the structure that you have in there, and you get really nice structures that that do appear. And there is a really a story about how these things can grow and remain, and that is obviously something that we match also in nature. So the question is, are these two dynamical systems actually comparable? And so to do this, we have to do a little bit of analytic matching to see this. But so if we look at this at these two equations, they definitely are both second order, and we can match them as follows. So first of all, we want to match the mean field evolution. To do this, what do we have to do? We have to look at the stupid neural network, a stupid neural network being one that does not depend on any data points, right? So this is just a constant in terms of data. So it doesn't depend on data, it depends on time. In this case, what happens with that neural network update equation, it just becomes this equation down here. Now, we can compare this, match this with the background equation. Namely, we can look at that equation also where h is not dynamical, h being the Hubble constant, Hubble parameter, in this case, we can do this when we are in a vacuum energy dominated universe, for instance. And in that case, these two equations do match, and you get a nice matching condition between the potential and parameters of the loss function. The NTK appears, and optimizer parameters do appear. Now you can go further, and you can compare how perturbations do well, because like a damped harmonic oscillator is not the most exciting thing necessarily. But what you can go about is basically you do a perturbation ansatz, and again, you are diagonalizing, you're decomposing your field into mean field, your neural network into mean field plus perturbations. And afterwards, you get to the algebra, you see these equations for the perturbations. Now, if you compare them with what you have on the cosmology side of things, they look a little bit different, but they are still nevertheless similar. And they are similar when, again, going into certain limits. So, for instance, when we can neglect these gradient terms, and the other thing is that we look at these eigenvalues, that they are that they're evolving slightly differently here. So, in that sense, this is there's definitely a nice analogy between these two systems, and we can ask, okay, yeah, are these is this actually working? Yeah.
Could you clarify the notation, like the dependence on the parameters versus the dependence on the data? Trying to understand who you're differentiating with respect to.
Yes. So this Fi is the number of modes with respect to data points, right? Okay. So if I have n data points, I've got n modes in the story. So this is parameters are not appearing here in that. So parameters are obviously in the F itself, but all these derivatives. So all these. So when I go to Fourier space, that Fourier space of data space. Does that clarify? Yeah.
Yeah, I guess I'm groping for where the usual learning in the space of parameters is described.
Yeah. So the usual. So let's go back to, so for instance, yeah, this equation here, right? So this equation is the update equation of the neural network that you're getting from gradient descent with momentum, right? I mean, if I go back to this slide, this is literally, this is the update equation you have for your neural network.
Okay, but the gradients in your analogy to perturbations and inflation are with respect to the data. Those are modes in the data.
Yes. So when you look here now, so in terms of the parameter update, right, this appears in theta, right? Right. So you see, I mean, this is where the information about the parameters is. Good. All right.
Sven, I also have a quick question. So the fluctuations you're doing, so the background is input independent. You emphasize it's a constant neural network, and then you're describing perturbations that depend on the input around the background. Is that right?
I will have general neural networks in a second. Yeah, but if you want to think about it, basically what you have a neural network, has varying outputs effectively.
Mm-hmm.
You literally ask, okay, what's the mean expectation? Yeah, that.
Yes, but to map onto the FLRW in the first place, you needed a constant neural network, and then you're doing input dependent fluctuations around it. Is that right?
No. So let's see. So here, this is a completely general neural network.
Can you just back up one slide or two?
So to do this,
no, the in between slide where you said constant.
Yeah. So this was just to match the.
There you go.
To match exactly the mean field in the first set of things. This was just to make the first thing for the.
And then you're fluctuating around this solution without input dependence.
No. So yes and no. Yes. Yeah. So because that's the basis we're looking at, right? So this is the basis that you're looking at, is basically here, right? So in this sense, you have a mean. You can always decompose your function of your neural network into a mean field plus perturbations. You can always do this. That's what you're doing.
Yeah, I mean, I guess there's a question of in which cases is it a small fluctuation around a constant, but
Correct.
you'll go to general neural networks in a
Yeah.
second. Thanks, I understand.
Yeah. But that will exactly, that's why it's good to do experiments and to see what's going on, whether that is actually something that is realized. So let's do this. So basically, and in the end, we're looking at examples where at this level where the modes are actually, not doing anything, they're frozen, as in the cosmology case for the vacuum energy. So what is happening here is now what we want to do is want to see whether this is actually describing the parameters, and basically also whether our matching of the EFT parameters on the neural network parameters, how do they look like? Yeah, what kind of numbers are we getting out? Yeah. And so you can ask, for instance, about in this constant case, okay, how does alpha look like? You pick a bunch of neural networks and you just literally calculate it. And what you do see is basically that you're covering various scales. And so this is mostly sensitive to, say, things like initialization, things like activation function don't matter too much. But that is what you're having. Now, and we're also doing something, just take a loss function, which is just quadratic. The other thing that we do need to check in this analysis was that we're actually in the right limit, namely that we are in a vacuum energy dominated contribution. And that's where we have to compare the respective scales between those things. And so you are actually in the vacuum energy dominated region if for reasonable amount of learning rates, right? So if this is important, because otherwise, you would not be in that limit, and that kind of would not be there. So, and you see, order 1 and standard learning rates are very much allowed in a large region of these parameters. So, and then you can go about and ask, okay, yeah, how well does this do? And this is shown to you here on the right, where we kind of do some examples in this case, where this is we measure essentially the difference of how much this mean field evolves, and compare it between the predicted dynamics and the actual neural network dynamics. And that is working nicely. What is shown to you in color, though, is something which is obviously the one thing that we will be interested in, is how much does alpha change during this period? And we do actually see that alpha does change. So alpha being the NTK, right? So this is the NTK at initialization, and this is in the end. So you do this for a bunch of networks, and you see these results. Then can go about perturbations. The story will be a little bit more subtle in the matching, but the most dominant feature, namely that these perturbations are actually frozen, you can demonstrate. Now, the next part, so this was kind of starting. So what we want to go at is basically we want to make these things use our knowledge about the data dependence of this story, and we want to ask whether we can make neural network training more important. And what's the basic observation here in this story? Is basically that we have a number of data points that sets a number of modes in the empirical NTK. But one crucial thing is obviously that the choice of data points sets which modes are actually chosen. So which eigenvalues do I see? And so the natural question is, okay, can we make training more data efficient by selecting good data points? And I mean, this is really clear because this is really important for the update of our neural network. Yeah.
Other
Yes.
version of the question before. So,
Yes.
yes. All right. Can I ask another version of the question from before really quickly? So there's a friction term in the training which has to do, and is that the Hubble friction here? But in inflation, there's a separate thing which is dilution in position space. And that's the, one way to think about the freeze out of the modes.
Yep.
So here, maybe this is a version of Jim's question. You have the Hubble friction in parameter space, but then you're also talking about the freeze out, which would be an effect of the dilution in, position space. So is it obvious that these two things should happen together?
Good. So for this part, I don't have to worry about Hubble friction, right? Because I'm not looking at friction. Okay.
I mean, I just want to make sure I have.
We don't have a complete picture of like the scale factor effectively, like where things are being happening and what the interpretation of that is. This is a super interesting question, yeah, to make that question. What I want to get across, and that's what we need to completely understand that story, and to kind of also, things like you can ask normal experiments about, how things evolve, whether that's a typical evolution of the scale factor, etc., that you were expecting of this story. What I want to get across to you now is literally we can already make headwind before looking at the dynamics. And before looking at the actual evolution of that system. By looking at it at t equal to 0.
Okay, but just to make sure I understand, the original analogy to Hubble was in terms of the gradient descent in parameter space. Is that correct? Do I have that right?
Yeah. Okay, it's a normal train. Yeah.
Okay.
There's nothing fancy.
Okay, so it's interesting that you're finding some effect of freeze out when those two things aren't obviously connected.
Yeah. So good. So good. Yes. So let's ask about the spectrum. Yeah. So let's ask here really, can we make this more data efficient? And to do this, we remind ourselves about this kind of picture, and to talk about this in a more unified framework is to ask, okay, are there good variables that we can actually ask for, that describe this spectrum in a architecture independent fashion and dataset independent fashion. And so what we definitely do see here as one feature is that the largest eigenvalue keeps dominating the whole story. We go across last. And this naturally suggests that we should look at this maximal eigenvalue, or respectively the trace of that object as one variable. Another thing that we think is very relevant in this case is the number of these modes and how they differ from each other. And so this kind of gives you kind of a diversity measure of how this training is going along. And a natural way to incorporate that is to look at the entropy measure of this story, which is given by normalized eigenvalues lambda log lambda of the NTK. And so what I want to explore is a little bit tell you about how these two variables correlate with neural network behavior. And so that's what we did. And so this is, for instance, for an MNIST task. You can ask, evaluate these two variables at the beginning of training and compare with the test loss after train, or the best test loss throughout. And that is shown to you here at the top right. And you see that, so these are all individual networks. They are dense networks here in this case that are being trained, all these data points. And you see that you get you see a trend, that you get better test performance if these variables are getting larger. That's what you do see. Now, what I'm showing you in the one beneath that is I'm coloring here the data set size. And you see also that for all that you see more data, obviously also seems to have an effect on this whole story. And that is what we are asking then is obviously, is this actually only hidden that this is more data, or is this actually something serious about these variables? And to decouple this, what we did is basically we went on to look at a particular data selection framework. Here, this is random network distillation. let me skip out of time explaining this. I'm happy to explain it second. But basically, the results of this data selection procedure is that for a given data set size, you end up with different collective variables, trace and entropy in this case. And you can run the same experiments on this story and ask, okay, what is the performance? And the performance is better when you use the data set with larger collective variables. So you do see that they have an impact on your actual test performance. So it's not just data set size that matters, but it's also the quality of data. It's a standard thing that we would expect. It's this with respect to these variables, we can find better performance. Now, yeah, so just to summarize this, so I think these variables are quite interesting to look at, and in particular also because they are obviously connected to physics and to in particular to statistical physics. Good. So now, last part of the talk, I want to talk a little bit about how can we use these collective variables to actually improve then our neural network dynamics, and to basically what we want to use them to optimize the optimizer. And that's obviously a very interesting field, and we have a lot of interesting talks in this.
Can I just ask a question or two on the last part?
Sure.
So good. So for the choices that apply to NTK, the empirical NTK is definitely sort of the right general thing to study, and looking for collective variables is very natural. But we've also heard at this conference some sort of different limits that are more mu-p-ish and so forth. I mean, is your perspective that even if you have a slightly different hyperparameter initialization that has sort of different scaling, that there's still going to be some kernel whose collective variables you should study, or is this sort of specific to NTK?
No, it's not specific to NTK. It's general.
Good.
So in that sense, because it's the thing is, I mean, this is we're not relying on this. I mean, on being in that particular limit. There's an interesting question on scaling these things up. Yeah. Scaling these things up to larger systems, etc. And that's obviously one has to look at carefully to see what's happening.
And real quick, the other question is so collective variables in the NTK are relevant for dynamics. At the end of the day, what we sort of really care about is the mean network prediction across the infinite ensemble as you converge time towards infinity, and also the variance. Do you have a sense of how?
I disagree with that statement, but I don't look at T equals infinite. I don't look at the average prediction. I look at actual prediction, and I look at it at a finite amount of time.
Good. So I also care about the actual prediction, the average. But I'm curious about how those collective variables feed into the prediction, and whether you've traced those contributions. That's my question.
Yes. So this is exactly that picture here, right? That's what you should take out of this, right? So if you have a network, and if you have so fix your architecture, for instance, right? These collective variables do feed in how good your prediction is in the end. You can measure this. You measure these variables at the beginning of training, and I can tell you, okay, let's look again. Yeah, so we can basically reshuffle. For instance, you can reshuffle your data set, yeah, or select your data set differently, and I'll tell you, okay, you most likely get from our empirical findings, we get better performance. Yeah, that's what these plan. Yeah, so there's not yet a complete calculation. Okay, why trace of 3.5 gives you this number, but this is just empirical.
But this statement actually relies on the NTK being frozen, right? I mean, you said you can generalize this to mu-p or whatever.
No, this is the actual network training. This is just evaluated at the beginning of training. Yeah. These statements are these are general networks trained. There's nothing done. You just evaluate these variables at the beginning of training.
And why don't they evolve during training?
They evolve during training, but I'm showing you the correlation at time equal to 0 with the final.
Okay, so then is there an intuition why sort of at training time equals 0? This is already, so if the if I'm on the top right of this plot, the training time t equals 0 and the NTK will change during training, why this was still sort of from the get-go clear that it will work?
It's not clear, and they actually do evolve when you measure these things, and that's exciting experiments we are looking at. But it is that intuition of NTK, or of the perturbativeness of things, that the first approximation, NTK at with 100 of dense networks or with 1,000 is actually a good approximation to the dynamics. Okay? So that's where that approximation can still be made.
I have a quick semi-clarification question on the last slide. Like my naive interpretation is that both the collective variables increase when you increase data, and that translates to the test loss also going down in the top plot. So does this roughly mean that like this is some predictor of the scaling with data, or does it actually have more information about the dynamics as well?
That's exactly why I was showing this experiment beforehand. It's exactly that's the right question to ask. Yeah, is this just more data? Effectively, what we're seeing, and the point is no, it's not more data. Yeah, it's not just more data, and that is because we have what we're doing here is basically we have a way of selecting samples, and these samples they have different different collective variables, right? So you have same size, higher collective variables, and you can correlate this very nicely with better test performance in the end.
So none of them were out of distribution, because one way of minimizing the entropy is to just show it once from the MNIST. One way of minimizing the entropy would be probably to just show it one digit from MNIST.
Yeah, but you want to have a large entropy.
Yeah, but I mean, so
and you
my
want
point
to have
is
a large
it might
entropy
be
with just 20 points, right? That's the question. How.
Yeah, but I mean, if it's performing poorly on the bottom left, let's say, that could be because you sampled such that most of the things that you're testing on are out of distribution.
Good. Yes, this could be, but this is exactly when you. So in this case, good. So you're asking exactly. So this if you so let me rephrase your question and correct me if I don't get it correctly. So I'm picking a random data set size of MNIST of 40, for instance. And clearly, as you see, this might not have all of the features that are in there, but I test it with much. That's absolutely correct. Yeah, that's exactly the point. Yeah, that you not getting a very diverse data set. Yeah, and so in that sense, this other data set, yeah, although it only has 40 points, yeah, you are improving the diversity in that data set. And the diversity with respect to that network, that's also important, right? It's not just the diversity of, some measure of the data itself, but passed through the network and evaluated via the NTK. Good. Yeah, let me talk about optimizing optimizers. And so this, let's set the scene a little bit. So this is basically, a way of biasing optimizers that we want to be interested in, and there are obviously natural ways of how you can think about this, and people have thought about it for a long time. One direction is in terms of natural gradient descent. The problem of this is that this is very expensive typically in the number of parameters, and that often we only have approximations of these available, and then there's also a practical issue is if you look at it in terms of the eigenvalues that actually contribute, then they're in Fisher, if they're very small, in the inverse step, that implies that you're taking a very large dramatic update. And so this can lead to instabilities of this story. And so that, per se might not be the most optimal thing in practice to be doing. And this has to be confronted with standard things like Adam that we are using. And so this is, obviously avoids this expensive Fisher calculation, but still has some information of this in the particularly the diagonal entries of Fisher are being used. And then you have, obviously also other modifications. And so what we want to look at is basically to look at things that kind of combine things from both, where we kind of, which we kind of call this class spectral optimizers, where we want to avoid the expense of calculating Fisher, but still use the spectral information in there. And so today I want to show you some results for using the largest eigenvalue, in particular here again the trace essentially of this object, and that's our trace optimizer. So why is the trace actually related with respect to Fisher? So if you look at the empirical standard way of evaluating the Fisher metric, you can see that if you're looking at the trace of this object, you see that the diagonal components of the NTK start to emerge. And then if you are looking at basically, you are also, if you're looking at a trace and you will sum over, obviously, of its components, there's obviously the loss function that the gradient of that appears there. But to first approximation, this is somewhat, especially if you diagonalize this story, you get the maximum eigenvalue again. That starts to appear, and this is motivated us a little bit to look at how we can, which role does the trace play in rescaling the learning rate, and as first very coarse feature of natural gradient descent to implement. So what in practice do we do? This is, we don't use to set a learning rate of 1, and what we rescale the gradient with is the trace of NTK evaluated at time equal to 0 divided by the trace at a given time, t. What I'm showing you here are some early results, and we obviously are eagerly working on other architectures, tasks, etc. But they look very interesting and really I think interesting to look at. So let me show you a couple of these features. So this is again MNIST on some dense network. And what do we see is that we do see interesting performances in comparison to normal SGD and in comparison to Adam. So Adam is shown to you in green on these plots, and our trace optimizer is shown to you in red. And as you can see here at the bottom here, that's a test loss, that we do look at. And in this case, so this is averaged obviously over lots of networks. That's what your error bars are giving you. And what we do see is actually a comparable behavior to Adam. But we see less overfitting effectively in this story, and by just doing this rescaling for this task, we can get at the performance of Adam. So from SGD to that really gets you already that far away. Okay, good. Let me conclude briefly, and then I'm happy to answer any questions. So what we think is that effective field theories are very good to framework to describe nonlinear neural network dynamics. They are, I think, connected to physical systems, and we can see that these dynamics can be approximated compared to scalar field dynamics in Friedman, Lemaitre, Roberts, and Walker in a vacuum-dominated case. We do see in this NTK framework and in this approach that there's a hierarchical suppression in the eigenvalues, and this leads to subspace of subspace only being relevant for the dynamics, and this can be addressed with collective variables. These collective variables that you can use then ask to use them in downstream tasks, and so here we use them for data selection, improving that, and to have a first look at using them for optimizers. So with that, yeah, let me thank you, and I'm looking forward to questions and discussions.
Thank you very much, Sven. We're running a little bit short on time, and we already had a lot of questions, so I'll take these two, and then we move on.
Yeah, when you were comparing this method to Atom, you plotted by epoch, but how does that compare to CPU time?
Very good. Yeah, it's still a bit in progress, and that's a very interesting question, because we obviously have to evaluate NTK, right, throughout this, and there is obviously a bottleneck at some point, so you have to do this quickly. And we actually there's a interesting scaling behavior of this in terms of the data, how many data points. So you can have nice phenomenological models for evaluating that trace, so that get you to fast speed for this optimizer. But that's exactly, yeah, one of.
Sven, can you go back to the previous slide for a second? I'm just trying to stare at the equations, and maybe you could make your. So you don't assume anything about the loss here, is that right?
I don't. So in order to, have these kind of things being completely justified, etc.,
Yeah.
right? Then you make assumptions. You would, see this being realized for certain loss functions. Yeah, up to here it's general pretty much, apart from that first thing, and then there are approximations.
So, okay, so can I interpret this in some senses? Natural gradient is good but slow, but it might have some collective variable in the Fisher information that you could design an optimizer just directly with that thing, and it happens to be directly related to the trace of the NTK.
Yeah.
Okay. And yours is faster because you're not actually computing the full metric and inverting, which is part of natural gradient. You're doing a fast calculation on a matrix, basically.
Yeah.
So it has, in some sense, the spirit of what's good about natural gradient without the downside.
Yeah.
Okay, got it. Thanks.
All right. In the interest of time, let's move on, and thanks, Sven, again.